be live now.
Hi, everyone, and welcome to this afternoon session of Human and Robotic Exploration Moon 1 session. We are missing our session chair at the moment, as well as our first two presenters. So we're going to jump ahead, and we are going to jump to Romain Martin, and he will start our presentation, and we'll line up our other speakers after that. Maybe by then we'll have our session chair and everything will be good, and we will just carry on. So Romain, over to you if you'd like to introduce yourself and continue with your presentation. Thank you.
Thank you very much. I hope you can hear me well.
Everything's perfect.
Okay, so thank you very much. So my name is Romain Martin. I'm working at ETS, École de Technologie Supérieure in Montreal. And under the supervision of Professor Christer Johansson, who's working at the Research Institute of Sweden in Göteborg, Professor Jason Robert Tavares from Chemical Engineering in Polytechnique Montréal, and Professor Martin Dubé, Mechanical Engineering at ETS. And I'll present you my work today on the benefits of joining thermoplastic sandwich structure using induction welding for lunar environment applications. So we have to put first a context. We are dealing with the lunar environment. Why is that? It's because my work is part of a project led by CSA called PEEKbot project. You have more information about that in a following presentation by Mr. Sura. But to summarize, this project aims to develop a PEEK-based lunar rover structure. And why is that? Mainly it's because of the thermal lunar environment that we are facing on the moon. A lunar day, which is the time when we are facing the sun on the moon's surface, lasts approximately 14 Earth days, during which the surface temperature reaches 100 degrees Celsius. But then it's followed by a lunar night, which also lasts around 14 Earth days, in which the temperature drops to minus 200 degrees Celsius. Of course, this is a concern for two main reasons in which we are focused here. The first one is that the structure and the parts will experience thermal expansion and contraction because of these thermal cycles, and this will induce mechanical stresses in the parts if they have different coefficient of thermal expansion, and that may lead to failure. And we don't want a failure like this to occur on the moon surface. But the other aspect is the thermal insulation. We need to protect the electrical equipment that's inside the rover to survive the long and cold lunar night, which has always been a challenge that has never been solved to date. So that's why this project is focusing on that. Typically, in the space industry and field, we are using a lot of sandwich structure. What is a sandwich structure? Well, basically, it's a low-density core it's a low-density core that is typically made of aluminum or Nomex, or can be also foams. But typically, it's in the honeycomb geometry, as you can see here on the screen. And this is surrounded by skins, which are typically either also aluminum or carbon fiber epoxy composites. And to link those materials, we have to bond them because we want to transmit the efforts. So we have to use a material, and typically it's adhesives. So an adhesive is a thermoset tapes. So as we can see, skin adhesive core, we have a multi-material system, 3 different materials with different CTEs, and that induces a risk of debonding in the structure, especially during thermal cycles as on the moon. So why are we interested in going for other material? Well, first, research done at CSA, and Mr. Sura will talk more about it, but show that using a 3D printed thermoplastic core could provide with a sufficient thermal insulation to provide protection for during the cold lunar night. And that's why it's interesting to go to thermoplastic sandwich structure. So the core, as I said, could be 3D printed thermoplastic honeycomb structure. And then the skin would be thermoplastic reinforced with carbon fibers. But then we have a challenge. How can we join the skin in the core in this thermoplastic sandwich? The main challenges are the following. We have to have a chemically compatible technique to join this thermoplastic part. We want it to be not exposed to thermal cycling, so have a similar CTEs, and also be low outgassing, which is a common issue in aerospace, especially in space because of the vacuum in the surrounding environment. So how can we do that? Typically, to join composites, there are a few families of technique. The first one, as I mentioned before, is the adhesive bonding. But as we can see, adhesive typically are thermoset material, which are not very chemically compatible with thermoplastic, usually requires an extensive surface preparation to reach proper properties. So we also see that thermoset and thermoplastic sometimes have different CTE, and the CTE mismatch, as mentioned, can lead to debonding and failure of the structure. And also many adhesives are outgassing. Some of them are not and are used in the space, but we are limited in the choice that we have. So that's why adhesive bonding is not the best way to join core to skins in thermoplastic sandwich structure. The second mainly used technique are mechanical fasteners, like bolts or rivets. But typically, as we can see, it's not adapted to a sandwich structure. We cannot bolt a skin to a core. And overall, we don't like drilling holes in fiber reinforced composites because this induces delamination or rupture of the fibers, and we don't really like that. It's a stress concentration area. Plus, the mechanical fasteners usually represent a weight penalty that we would like to avoid. So for those reasons, mechanical fasteners are not adapted. So what can we do? These two major techniques are not adapted to us. This is why we go for welding or fusion bonding techniques. Here, the advantage is that it's chemically compatible because we use thermoplastic versus thermoplastic. We don't put a foreign material like thermoset that is not chemically compatible. There is no CTE mismatch because of that. And it's also adapted to sandwich structure because it can be welded on any, you can weld on any type of surfaces. So if we dig deeper into the fusion bonding techniques, here's what we can see. We have various fusion bonding techniques that exist. Most of them, as I was saying, have no CTE mismatch, especially when we don't use any foreign material as a heating element at the joining interface. But most importantly, when using fusion bonding technique for thermoplastic materials, is that we don't need any or very little surface preparation compared to the extensive etching or grinding that is required for adhesives to be used with thermoplastic. So that's a major advantage. And as we see, using fusion bonding in thermoplastic material have two main potential that I would like to explore today, are the potential for skin core adhesion in structures, in sandwich structures, but also a potential for repair of thermoplastic parts. And I will come back to that in a moment. So in my project, we are focusing on induction welding, which is one of the commonly used welding techniques. So how does induction welding works? It relies on the application of an alternating magnetic field to generate heat at the joining interface. And that will melt the surrounding thermoplastic that will be able to be consolidated under pressure to form a bond. There are three main strategies to do so. The first one is to generate eddy current or induce eddy current directly into the adherent. This can be done when the adherent is made of electrically conductive fibers, such as carbon fibers, and in an architecture that allows for the formation of closed loop of currents. So for example, the 090 architecture will do that. In that case, in the presence of an alternating magnetic field, you will induce eddy current in your material and melt the thermoplastic. The major issue of that technique is that first you have to have electrically conductive fibers in an architecture that satisfies the geometries, but also we realize that most of the heat is generated throughout the thickness and not only at the joining interface, but also most of the heat will be at the outer surface of the upper adherent facing the coil. So we cannot really locate the heat dissipation with that method. So that's why there is a second technique where we put a material called a susceptor, in that case an electrical susceptor, in which the induction of eddy current is more favorable than inside the adherent. This can also, of course, be used in case of non-electrically conductive fibers, such as glass fiber, for example. In that case, the eddy currents are really generated at the joining interface, so you got localization. But the problem is these susceptors typically are metallic mesh or carbon fiber fabric. So you are introducing a foreign material at the joining interface, which has clearly a different CTE than the thermoplastic. And so that can create a delamination and problem during thermal cycling. So it might not solve the issue. So that's why we are in my project focusing on a third technique, which is to rely on hysteresis losses in magnetic material. So this time the susceptor is called hysteresis losses susceptor or magnetic susceptor. And it relies on the fact that magnetic material, when they are experiencing an alternating magnetic field, will actually get magnetized and demagnetized, or magnetized in the opposite direction. And you'll typically have this hysteresis here, as shown here, and the surface area of this hysteresis actually corresponds to the fraction of heat that is absorbed by the material and released into the form of heat. So it's possible to use that property to generate heat at the joining interface. So what do? We mix magnetic particles inside the thermoplastic to produce a film that will be placed at the joining interface. And that way it's possible to weld. How do we weld and then how do we generate heat? Well, this is the only equation of my presentation. What is really important here is that it's the equation for the heating rate of an isolated sample of susceptor. So we're not considering any boundary condition or thermal losses in the environment. But what's important to see is that it relies on a few parameters. The first two are process-related parameters, which are the frequency of the alternating magnetic field and the volume fraction of the particles that you disperse into your film of susceptor. The other parameters are all materials-related parameters. We have the density and the specific heat of the thermoplastic matrix, same properties for magnetic particle, and also a parameter called the absorbed energy density of the magnetic particle, which corresponds to the surface, the enclosed surface area of the hysteresis that I was just talking about before. It's interesting to note that this last parameter, the absorbed energy density, is related to the magnetic field amplitude. So even though the magnetic field amplitude does not directly appear in the equation, it's actually a very important process-related parameters to quantify. So once we have all this, we can predict what will be the heating rate of a susceptor. But it's important to note one thing. All these material-related parameters are a function of temperature. So the more you will heat up, these properties will vary. So it will be harder to keep track on the temperature at the bond line. And that's the major challenge of any type of welding, and induction welding is also in that case. So once we have a susceptor that is possible to be used and that can heat up an interface, how can we use it? Well, it has the potential for skin core adhesion. Back to my scheme of before, now we know what we can put between the skin and the core. We can put a susceptor film and use it to bond skins to core in thermoplastic structures. And that way, by applying a magnetic field under pressure, consolidate a thermoplastic sandwich structure. So that's a very huge potential to allow for the use of all thermoplastic sandwich structure, which, as we mentioned before, have very major interest in the lunar surface. But there is another potential for induction welding. It's for repair. Well, let's first talk about repair in orbit. A few months ago in May, Canadarm2 was hit by a space debris. As you can see, the impact here was located near the elbow of the arm, and it's actually caused damage. And we know that Canadarm2 was made out of carbon fiber PEEK tubes. And what we observe typically with those type of damage, this is a section of similar to Canadarm, we see that we have the primary damage, which is the point of entry of the projectile or the debris. And then we have a secondary damage at the other side, which is like the cloud of debris of the primary damage that impacts the other side. All of this must be repaired. And in orbit, we can repair it if we want to repair it by using patches or technique like this. And I will come back to it in a moment how to do that. But how can we transfer that to the moon? Well, if we want to go to the moon, the major issue are not space debris, but actually meteorites. The lunar surface is hit by little to large meteorites a lot of time, many times a day, and we don't have protection for that. So the strategy as of now was always like to hope for the best.
Romain, you're at 15 minutes now, so
okay.
we're into question period. Perfect. Keep going.
So we will have to do some repair on site, and to do so, we can use repair techniques that were developed in my group, which are like patch repair and using actually induction welding, and especially work from Mr. Cote showed in a structure similar to Canada that it was possible to repair carbon fiber PEEK structure using induction welding. So it has a very large potential for repair also on the moon. So to conclude, I showed to you today the benefits of induction welding that has the potential to join skins to core in sandwich structure and also to repair thermoplastic composite parts. The key challenges are the ferromagnetic particles distribution, to control the temperature at the welding interface, and to apply joining pressure during welding. And our goal in that project is to explore and apply these potential benefits to the future Lunar Rover in the frame of the PEEKbot project. So I'd like to thank you very much for your attention.
All right, thank you, Romain, and apologies, I joined the session a couple minutes late, and I missed the start, but thank you, Todd, for taking over my duties. So my name is Dr. Michele Ferragelli. I'm the Chief Technology Officer of Mission Control Space Services, and I'm the session chair for this one. So thank you, Romain. I didn't see any questions in the chat window, but I have a question for you, if you don't mind.
Please.
So the idea of repair in situ is really exciting and interesting, I think, especially as we look towards building a sustainable kind of in-space infrastructure on the moon and in our orbit. Have you considered not just repair, but also manufacturing and assembly in space so that you can kind of get around the limitations of size, of course, of launching things into space on a rocket? And if so, what are some of the considerations in terms of design if you want to do that?
Yeah, so in my group, like for now, we are more focused on assembly, like on Earth. But of course, it opens the opportunity for repairs on the moon. And if we even go further, like on the moon, we could imagine that you could have send a repaired part or a replacement part in a few weeks, maybe. But in the future, if you would like to go to Mars, that would take months. So you could not you cannot accept to be not able to repair or build a new part. And that's why also it's very interesting to put that in a parallel of 3D printing, because as I mentioned, we want to use 3D printed core structures. And I think with that, it gives the opportunity to build part, to manufacture part, imagine on a lunar base, and even to repair it or to replace it, because some parts will not be repaired, but you could replace it. And if you're able to build a new part by 3D printing on the moon surface, put it on your rover and attach it and weld it by induction, then you have a replacement part. And you are allowed to continue your exploration and your mission. So that is very interesting. For the limitation, I think at the moment, one of could be a limitation is just the power supply. But I guess we are right now working with relatively low, I would say, power compared to other joining techniques. So I guess it could be solved in the future if we wanted to have like a workshop on the moon base that could build an assemble part like this.
Very cool, very cool. And we have another question here in the window from Pierre-Alexis. I don't know if you could read it there, Romain. Can you see that? Or I could read it for you if you want. Yeah. In terms of power requirements, what would be the approximate scale of the power required by the induction welding process? And how scalable would it be between small and larger repair and manufacturing?
I would say right now we have like something around 10 kilowatts for the generator we have. It's relatively small ones compared to some you could find in industry, induction heating setups. So I would say something around that. About the scalability, it also depends on how fast you want to go. Of course, if on the moon, on Earth, we are used to producing series and we want to go very fast. So of course, for that, you would need like more power to produce more heat and go faster. But maybe on the moon, we could be a little more patient and do larger repair at a smaller rate, but with a smaller power supply. So I guess even a small power supply could do large manufacturing and repair and assembly, as long as you maybe give it a bit more time to do it. But it's possible, I think, to scale it up even on the moon.
Great, thank you very much. All right, well, thank you, Romain, and we will move on to the next speaker now, who is Jose Arnal. I don't know if I said your name.
Yeah, that's fine.
That's right. Okay, and the title of your topic is Three-Dimensional Ideal MHD Simulations of the Lunar Space Environment.
Okay, great. And sorry, excuse me, everyone, for the delay. I'm just having a lot of technical issues with feed loop, but hopefully everything goes well. So as mentioned, my name is Jose Arnal. I'm a UFD student under the supervision of Professor Groth. And today I have an exciting talk titled Three-Dimensional Ideal MHD Simulations of the Lunar Space Environment. So a lot of what I'll be talking about in this presentation is simulations of space weather. And space weather are these phenomena that occur in outer space that often have adverse effects on humans and technology. So for example, these events can cause problems with the power grid. They can cause satellite operational problems. They can cause interference and disruptions to communication and GPS navigation systems, et cetera, et cetera. So we're really interested in forecasting the space weather so that we can mitigate these risks, or at least help mitigate these risks. Now, the main motivation for today's topic will be man's return to the moon. So there's the planned Lunar Gateway, which will have on board NASA's Hermes and the ESA's Ursa, which are instruments that target to improve space weather forecasting for our Artemis astronauts returning to the moon. And the Lunar Gateway will really be an opportunity to use or to have access to observational data from these missions, which will provide a unique opportunity for heliophysics and space weather related studies using the framework that I'll be presenting today. And it also will give rise to, or at least opportunities to do lunar related science. So for example, to characterize the lunar plasma environment and solar wind interactions with the lunar surface. In particular, what we'll take a look at today will be essentially there's been some recent studies and some recent observations that suggest the occurrence of a bow shock upstream of the Earth, or a so-called mini magnetosphere, and that arises from the interaction of the solar wind with crustal magnetic field anomalies. So we'll want to simulate those. And if we're interested, again, in understanding the physical processes at the lunar surface, numerical simulations can really play a big role in this. They can help by providing baseline characterization of the lunar environment before it's perturbed by humans. And it can also be used to simulate observations from planned missions before the missions are even carried out. It can also fill in the gaps where observations may not be available or practical. And by observing the discrepancies between the observations that we do make and the simulations that we study, that might provide avenues to further improve our models and our theoretical understandings. So in this presentation, I'll be presenting a space weather forecasting framework, and then we'll be using this framework or adapting this framework to study the lunar space plasma environment in particular. Now, there's a recent publication by a previous student in our research group, and here he published the framework that I keep talking about, which can accurately capture a range of solar wind and heliospheric phenomena, which I'll demonstrate. In combination with observational data and measurements, this framework provides a basis for theoretical studies of space weather. And the use of the framework for operational space weather forecasting is currently being investigated at the Canadian Space Weather Forecasting Center at the Natural Resources Canada. Now, just to give a brief overview of this framework, it's essentially broken up into a series of models. In the lower corona, from the surface of the sun to 25 radii, we use two field source models. And then from 25 radii all the way to 215 solar radii, where the Earth is located, we use magnetohydrodynamics model, or MHD. And then to couple these two models, SCS and the MHD model, we essentially use an empirical model that gives us solar wind parameters from magnetic field simulations. And all these, and the PFFS model, or the PFSS model, is ingest boundary conditions from essentially from photographs of the sun. So there are photographs that are produced of the sun, and then from these photographs we can extract the magnetic field, and we call these magnetograms. And this framework is really at the forefront of simulation technology worldwide. It uses cubed sphere grids, which allows for a full 3D coverage of space without polar singularities, and that's what I'm showing here on the left. It has the availability of using high-order finite volume spatial discretization. It makes use of anisotropic block-based adaptive mesh refinement, and it's been implemented massively parallel. It can be run on up to 30,000 cores. Now here's, for example, some boundary conditions that again are derived from these magnetograms, essentially at the solar surface. And then with these boundary conditions, we can, using this framework, we can extrapolate all the way to where the Earth is located. And here I'm showing the magnetic field in essentially this sort of global heliosphere. And we also show how our adaptive mesh refinement can really refine the mesh automatically to capture areas in the flow that are of interest. And by just a note, these are not cells that you're seeing, these are blocks. Each block then contains a multitude of cells. So for example, if we start on the coarsest mesh, we see that we get an overall coarse view of the heliosphere. And then as we refine, we get a much more refined view. And for example, we can see the presence of a current sheet here in blue. Just as a note here, we're using, for example, 73,000 cells. Well, when we refine, our simulations now taking place with 23 million cells. And here I'm showing the steady background solar wind, and I'm showing in particular the solar wind speed. And we can take a few slices to sort of see what this sort of the inside of the sphere looks like. Well, here in the middle, we would again have the sun. This brown dot here represents the Earth. So we see how we can get a background sort of forecast of the solar wind near the Earth. Now, what I showed before was all steady state simulations, but we can also do unsteady simulations. Whereas in the steady state simulation, we would use just one magnetogram. When we run unsteady simulations, we essentially use a multitude of magnetograms. For the results that I'll show today, we use 64 consecutive magnetograms, and the simulations are over the span of 16 days, from the 18th of January to the 2nd of February in 2007. So here we see essentially different slices of the ecliptic plane at different points in time, where again, the sun would be located in the center here, and then the brown dot represents the Earth. Just a note that in this frame of reference, the sun actually is fixed and the surface doesn't spin. And that's why we see sort of the Earth spinning so much. And we see how at about 440 hours or 490 hours, we see the Earth sort of entering into this high speed solar wind stream. And when we compare our framework with observational data, we see that we get quite decent results. So for example, here I'm showing our MHD simulation in blue versus data from the ACE satellite. And we see that although we're not perfectly capturing the solar wind, we're still able to reproduce sort of the main structures, although there's definitely room to improve our model. Here, I just want to also again highlight the sort of efficacy of our adaptive mesh refinement strategies. Here we see 4 CMEs, or coronal mass ejections. We have one here, one here, one here, and one here. And these 2 plots are at different times. And we see how our AMR strategy is able to really refine the grid at the sort of shock front of this CME. So those are encouraging results. We can also compare against observations at the Earth. So for example, in black here, I'm showing the solar wind speed at the Earth versus our models in blue and red. And we see again that we're not perfectly capturing the structure of the solar wind, but we're still able to do quite well, I would say. Now, sort of moving now towards the lunar simulations. Just one note, I want to talk just briefly about the MHD equations. I've mentioned them a few times. So for any of you that are familiar with computational fluid dynamics or the equations of the other equations of gas dynamics, the MHD equations essentially describe perfectly electrically conducting, fully ionized quasi-neutral flows of a compressible plasma. And these equations essentially are formed by coupling of the Euler equations of gas dynamics and the Maxwell's equations of E&M. And we essentially have the conservation of mass, the conservation of momentum, the conservation of energy, as well as the time evolution of the magnetic field. So for our lunar simulations, we're sort of flipping this framework sort of upside down, where instead for the heliophysics simulations, we had our boundary conditions really sort of coming in from the sun. Now we're sort of imposing these inflow boundary conditions on the outside, on the sort of upstream phase. And then on the downstream phase, we have extrapolation boundary conditions. And then this tiny little sphere here corresponds to the moon. So on the upstream phase of the moon, we have absorption boundary conditions. And then on the downstream phase of the moon, we also have absorption boundary conditions, but we reflect the velocity vector. And just a note that this initial computational mesh is only comprised of 73,000 cells. However, as we refine the mesh, we'll get a finer mesh, of course. Now, to study the interaction of the solar wind, we're going to use sort of typical solar wind conditions. So, for example, in this simulation, we're using a solar wind speed of 461 kilometers per second and a number density of 7 particles per centimeter cubed, a temperature of 2.5 times 10 to the 5 Kelvin, and we're also imposing a interplanetary magnetic field. Now we're only imposing the magnetic field in one direction, in the Z direction, so sort of along this axis, and it has a magnitude of 7 nanoteslas. Now I mentioned before that we also wanted to explore these sort of anomalous crustal magnetic fields that can give rise to these sort of mini magnetospheres. So to do that, as a sort of a first simulation, we essentially just imposed a tiny little dipole that's buried just beneath the surface of the moon. So the moon here is shown by this gray circle, and this black dot is the location where the focus of the dipole is located. So here is sort of the wake in 3D space that we get from this simulation. And I want to bring your attention to really 3 planes. So I want to bring your attention to the y-x plane, which is this plane, the xz plane, and then also the plane, the yz plane here, that's showing us the wake. And we're going to look at those in more detail. So in the top 3 figures, I have the number density in the planes that I just mentioned. And then in the bottom figure, we have the magnitude of the magnetic field. So we see right away from these results, we sort of see this prototypical lunar wake that we would expect. If you've ever sort of looked at textbooks of the lunar wake, this is sort of the image that are usually shown. One interesting thing that we see on the ZX plane, because of this, the magnetic field in the Z direction, we see sort of a diffusion of the wake, whereas in the YX plane, it's much sharper. And then when we're looking at the wake, again, because of the presence of the magnetic field, we see an asymmetrical wake, which is what we would expect. And then we also see similar results for the magnitude of the magnetic field. And of course, in this ZX plane, we see much higher magnitudes. And these results are for the case when we don't have a dipole, right? Now, I also want to talk about the AMR scheme that we're using. So we see that upstream of the moon, where really our mesh is quite coarse because there's really no interesting flow behavior happening there. But downstream, where the wake is, we do see the mesh refining quite finely around the wake. So again, these are encouraging results to see for a model. Now, here we have similar results now, but we do actually include the dipole, and we see the presence of this tiny little bow shock that's in front of the moon, and that's what we see in observations. So it's encouraging that we can mimic this behavior by using this dipole. Another interesting thing to note is that now our wake is asymmetrical both in this direction as before, but now also in this direction, and that's because of this the asymmetrical position of the dipole. And then we can also take a closer look at the magnetic field. So here I'm showing the ZX plane, sort of just zoomed in, and we see also magnetic field lines, and we can, by looking at these magnetic field lines, we can appreciate the sort of asymmetry of the wake better. And again, we sort of see this sort of mini bow shock forming in front of the moon. Now, in summary, we demonstrated the potential for use of a unique made in Canada heliophysics framework in combination with future observational data arising from the Lunar Gateway missions to improve significantly our understanding of the heliosphere, the geospace environment, the lunar space environment, and beyond. So, for example, in the future, we could consider other planets for future planetary exploration, and for also improved space weather forecasting. Now, going in the future, we'd like to also develop data simulation techniques to allow the ingestion of observational data arising from spacecraft and ground-based instruments, and this will really sort of help take our model to the next level, and hopefully be able to match the observations that we have much better. We also hope to improve the modeling by the inclusion of the influence of dust on lunar flows. So all the simulations that I showed today didn't account for dust on the lunar space environment, but that's something that we could consider in the future. We also plan to explore more realistic crustal magnetic fields. So in this work, we just imposed a small dipole, but this is not necessarily a very physical a model of these anomalous magnetic fields. So there's some work to be done there. And then finally, it'd be great if we could couple the space weather forecasting framework that I presented with the lunar space plasma model that I also presented. So now they're sort of separate, but if we could couple them so that we get boundary conditions and initial conditions from the space weather forecasting framework for the lunar space plasma model, that would be great. And that's all I have for today, and I'm open to any questions.
All right. Thank you very much, Jose. We have a couple minutes still available for questions. So if you have any questions, please put them in the chat window. Maybe I'll give you one. I mean, we only got a minute till the next presentation, but can you talk a little bit about how forecasting works a little bit for space weather, and how how do you use this modeling for predictive analysis, and presumably how that impacts space systems, human space flight, and things like that?
Right. So as I mentioned at the beginning of the presentation, this work is sort of currently being investigated at NRCan, Natural Resources Canada, to use in a sort of operational setting. Right now, it's not necessarily used operationally yet. So, we don't have frequent sort of simulations. But once this sort of gets going, the way that it would work is that we would get these magnetograms, so these sort of photographs of the solar surface, and we would get these magnetograms days in advance. This would allow us to run our simulations, and then from these simulations we would get sort of solar wind conditions at the Earth. And then if this were to be explored more, then with these solar wind conditions at the Earth, then you'd be able to use sort of more local models that look at just the sort of environment around the Earth and then you could, using sort of what I guess what I'm trying to say is that our framework would sort of provide these sort of boundary conditions to more local models.
Great. Well, thank you very much, Jose. So we'll move on to the next presenter now. I'll loop back. I think presenter number 2 wasn't there initially, but is Pierre-Alexis Joumel online? Looking here, I don't see him, from Airbus. Okay. All right. Well, if not, then I think we'll jump to the fourth presentation, which is PEEKbot, a 3D printed thermoplastic rover to survive the lunar night. The presenter, I believe, is Anton. Yeah, there we go. Hi, Anton. All right. Well, feel free to take it away, Anton. Anton Sura from, I believe, the Canadian Space Agency, if I'm not mistaken, right?
Yes. Hi.
Excellent.
Can you hear me okay and see my presentation?
Yeah, looks good. I'll turn mine off.
Excellent. Well, hello, everybody. My name's Anton Sura. I'm an engineer working for the Canadian Space Agency, and I'm going to present Marie-Josée Province and my work on the PEEKbot project, which is a 3D printed thermoplastic rover to survive the lunar night. She regrets she couldn't be here today, but she had a family emergency. But without further ado, I will move on. So the PEEKbot project itself was initiated when we realized that we don't have the means to survive a lunar night or in a permanently shadowed crater without nuclear power. And by we, I mean a lunar rover can't survive this situation. And so in brainstorming solutions to this, we have to investigate exactly what we'd be suggested to. And so Romain mentioned this previously, but I'll go over it again quickly. The temperatures on the moon are quite extreme, as well as the fact that they're long plateaus and the transition between the two temperatures can be quite brutal. And so the lunar night lasts for just over 2 Earth weeks, and the temperature can be as low as -200, and as soon as the sun comes back up, it very quickly shifts for another 2 weeks to 100 degrees Celsius. And so naturally, we wanted to do a thermal analysis to investigate what we could do in terms of surviving these brutal situations in order to have any mission that could last longer than just the 2 weeks available during the lunar day, as well as potentially investigate missions that could go into these permanently shadowed areas of the moon. And so based on our preliminary analysis on a classic aluminum rover, survival is completely impossible. Despite continuous 10 watts of heating over the course of the lunar night, the batteries still drop to -60 degrees Celsius. And this is below the survivability temperature of the batteries that we were considering at the time. And so despite the MLI, which is a multi-layer insulation blanket that would be draped over the rover, heat is still conducted through the structure to the wheels, as well as the fact that 10 watts of continuous heating over the night implies a huge mass, 19 kilograms of batteries for a 50-kilogram rover. And that has implications for the available equipment for the actual mission itself on the rover, and as well for the structure of the rover would need to be very highly optimized in terms of mass. And so one solution that was possible is to look into the field of composites. Composites have been used in the space domain before, but the usual main interest is to reduce mass. However, in this case, it could be beneficial for thermal management as they have very low conductivity of heat. However, these composites also raise concerns about their behavior at super frigid temperatures like -200 degrees Celsius. And so a study was done by Mathilde Jean Saint-Laurent at Laval University, and she found that while the material properties are diminished at this -200, they actually don't cause catastrophic failure at impact. So a rover rolling along or being impacted by a small meteorite at night wouldn't necessarily experience complete catastrophic failure. However, these classic honeycomb panels, as Romain brought up, the Nomex core with composite skin honeycomb panels do require an adhesive to be manufactured. And so this coefficient of thermal expansion mismatch remains a challenge. And so to avoid the introduction of thermal stresses from this mismatch, we looked to additive manufacturing. The bulk of the work for this project with regards to additive manufacturing has been done by Clément Brugui and Olivier Duchesne, as well as their professors Daniel Thériault and Frédéric Gosselin at Polytechnique Montréal. And I'll speak a little bit more about their work in the project later. However, the choices of composites is also restricted greatly by the outgassing properties. And so we can't just use any material we'd like, as in void, materials outgas. And so to avoid losing their mass and having them cover sensitive electronics or sensors, we have specific guidelines that the materials have to respect, and that is having a total mass loss of less than 1% and a collected volatile condensable mass of less than 0.1%, so quite low. So with regards to those constraints, we decided to investigate PEEK as a option to build a complete rover out of PEEK, and thus was born the PEEKbot project. This officially started in 2018 and includes several professors from 3 universities, as well as collaborations with several industrial partners. And the CSA, the Canadian Space Agency, has also been providing lots of mentoring on space and has also been sponsoring capstone projects for last year engineering courses. So this would be a 3D printed structure made entirely of PEEK. And this allowed us to open up the avenue to all kinds of different possibilities, not just surviving the night, but also being able to enhance the polymers and to have in situ repairability, as Romain again talked about before. However, to begin this project at all, we want to make sure that switching to PEEK with its very low thermal conductivity and appropriate material properties, that we would be able to simulate the honeycomb panel, and that these PEEK honeycomb panels would even be able to survive the night. And so to that end, a study was done on the effective thermal conductivity of a sandwich panel like the one shown here. And by assessing all the different possible geometries of honeycomb cores, as well as the shape of the panel itself, the thickness and the skin thickness, we were able to get the effective properties of an appropriate honeycomb panel that we could use. And so looking at the results of the thermal simulation itself during the lunar night, we found that the minimum battery temperature with just a purely PEEK structure actually raises it up from the -60 that we saw with the aluminum to just over 0 degrees Celsius, which is in the operatable and the survivable ranges for the batteries, as well as for most of the electronics that would be used on the rover. One important avenue of heat loss is through the wheels, as the heat gets radiated away towards space. And so one consideration to actually further improve the design was to replace in the drive system the couplings from the PEEK structure to the wheels with PEEK as opposed to aluminum. And that further increases the minimum battery temperature seen in our simulations, but that could also be considered as a method of reducing the amount of heat generation needed during the night, further reducing the mass of the batteries and allowing more flexibility within the rover itself. And so following that, we also did a random vibration analysis study. This was a vibration induced at launch, or the similar vibrations that would be induced at launch, and that are then transmitted into a ring that attaches from the lunar rover to what would be the lunar lander. And so we can see from the simulations that the largest concentrations of stresses are around this attachment ring, as well as around most of the inserts on the sides and bottom of the panel, creating attachments to both the wheels and the body of the rover itself. And so with that in mind, a study was launched with respect to this ring so that someone could look at the simulations, as this is a 2D plate representation of the base panel. So a study is being done to make sure that we understand how the strains are transmitted through the honeycomb panel, and that the cell walls that are adjacent to this ring won't be compromised by the launch. And that study will also investigate possible optimizations of this base panel in order to further reduce the vibrations and to improve our survivability and our performance at launch. One point, again, is that the inserts are an essential part that could potentially destroy the entire project. On the right, you see an example of a PEEK and Nomex core structure that was done by Stelia and Mirabel. Sorry, not PEEK. The composite here is carbon fiber and epoxy 9772. And so you can see that this does also have inserts in order to create the structure. And these inserts were done in titanium and aluminum. And so these are, again, major heat loss points as they radiate directly out into space and conduct the heat along the surface towards the wheels. And so work is actually currently being done on PEEK inserts that's being done at Polytechnique Montréal by Charles-Olivier Poiré and his professor Louis Laberge-Lebel. And so once we understand the properties of these PEEK inserts and establish their usability in the space environment, then we could again further reduce the amount of heat loss and really improve the thermal performance of the rover structure. And so kind of to summarize, the PEEKbot team is investigating many different interesting aspects that the 3D printing and the inclusion of PEEK has brought to the project. So one that's being done at Polytechnique is the capability to print on non-planar surfaces. This further increases the flexibility that 3D printing can bring to the structure of the rover and maybe not confine us to the classic box shape that we've always seen before. Other work has been done on the radiation protection and electrical conductivity of the PEEK, as the environment on the moon is constantly being bombarded with neutrons and other radiation that could be ionizing. And so in order to prevent the buildup of charge on a non-conducting surface, additives to prevent that have been studied. They've also been studying the modification of the properties of the PEEK by either blending it with other promising thermoplastics or including reinforcements such as carbon fibers. And those have been studied extensively as well at Polytechnique and at ETS Montréal. The PEEK inserts and bolts are being studied, as well as the induction welding of PEEK that was mentioned before. And finally, modeling of the 3D printed panels is also being studied in terms of both its structural properties, just in the quasi-static case, and the damping during the vibrations. This is important as the potential of the 3D printing to remove some of the bolts or inserts has also potentially removed a lot of the damping that you can get at launch. And so in order to evaluate the damping, the material itself has needed to be qualified, and currently being investigated is methods to improve the damping of the panel just through the honeycomb structure itself. And so bringing all this together into one huge project has been a large endeavor at the CSA, and we're very much looking forward to seeing where it goes from here. And that is everything I have for you. I don't know if there are any questions, but I'd be happy to answer them.
Great. Thank you so much, Anton. It's really great work, and it's nice to see CSA engaging with so many different industrial and academic partners as well. So I have a question here in the chat. I don't know if you can see them, but I could read them.
Yeah, if you could read them, that'd be great.
Oh, wait. I'm not sure if this is relevant. No, it's a question about nuclear power. I don't know why.
There was a quickly mentioned at the beginning of the presentation that
gotcha.
nuclear was trying to be avoided.
Gotcha. Okay, so yeah, so regarding nuclear power mentioned at the beginning of the presentation, just a quick comment on the Rolls-Royce is working on a portable nuclear power plant greater than 220 megawatts, transportable by truck that just so happens to fit within the Starship, 16 meters by 4 meters. Look at that.
That is really exciting. That's a pretty cool idea to have a portable power plant for sure. With regards to the Lunar Rover, the main concern with the nuclear power is that during launch, it's quite a bit more dangerous. We're trying to avoid the possibility of contamination if by whatever chance the rocket explodes or anything should happen to the rover on the way up. So that's one of the primary reasons we're trying to avoid nuclear, as well as the fact that in this case, the nuclear power plant is probably a bit too big to fit on the rover as well, because this is a miniature-sized rover, just planning on having a footprint of 700 by 700 millimeters. So quite undersized compared to other classic lunar rover pictures that you might have seen of the Apollo missions.
Absolutely. I don't see any other questions, but I definitely have a couple. It's a good presentation. I'm curious to know, you mentioned survival of the night. Were you talking about storage survival or actual operations at night?
In this case, we're looking at just survivability of the night, and so the rover would enter a keep alive state in order to really limit the amount of battery power that we need during the night, and so we can dedicate as much of it as possible towards heating the rover itself. Yeah, so that's where the focus is right now. The idea would be to go up for, say, a 6-week mission and have a two sets of lunar days to work with, as opposed to just the one that we've been limited to up till now. But if the project is ongoing and we determine that even more thermal optimization can be done, it'd be very exciting to see it survive the lunar night or in one of those permanently shadowed areas.
Yeah, for sure. And you mentioned -60°C as like too cold, I guess, for storage survival. What is your target? I know sort of electronics, that's probably not too bad of a range, but you mentioned the batteries that was too cold. Is that?
Yeah, it definitely depends from battery to battery that you're using, but the ones that we were investigating for the purposes of the study, I believe the survival temperature was at -10°C.
Oh.
Yeah, so quite a limited range. The benefit there was just extreme storage density, energy storage density, so that again, reducing the mass so that more scientific equipment could be fit on the rover.
Right. I guess maybe I'll indulge myself with another question. You mentioned PEEK being a great insulator, so being a good strategy for storing some heat during the night. What about during lunar daylight operations, particularly at equatorial regions and areas where it actually gets a little hot? I mean, hot is relative, but certainly the insides of the rover can get hot.
For sure.
Situations as well.
Yeah. So the idea of the rover is to have one of the projects that the CSA brought to Queen's engineering course was actually to just find a method to detach a radiator during the lunar night or lunar day, either dependent on like the temperature or in a mechanical way, being able to detach the radiator from the main body of the rover so that during the day you could radiate away that heat as much as possible and have it be connected to the most sensitive parts to that heat, like the electronic components and the batteries. And then during the night, when you want to keep as much heat as possible, to detach that radiator or fold it in a way that that prevents it from radiating the heat back out again.
Very cool.
Mm-hmm.
Yeah, and I can see these applications certainly being, or this material being applied to other things other than lunar rovers as well. So that's great. Okay, well, I don't see any other questions. So thank you very much, Anton, for stepping in to fill Marie-José's shoes. But it was a great talk.
Sure. Thanks very much.
Yeah, and so I just want to check one more time to see if our presenter from Airbus, Pierre-Alexis Joumel, is online. I don't currently see him at the moment, but if he's not there, then that would be about it for this session. We would end a little bit early. So I'll give him maybe another minute or so, but yeah, unfortunately, the talk on Lunar ISRU would not be available otherwise. But anyway, hopefully we'll have some other interesting talks in this session of human and robotic exploration. So tomorrow, don't forget to join us for some of those talks. There's one session focused specifically on the moon, again, much like this one. I think a bit more slant towards mobility and navigation and artificial intelligence, and then another session more on space exploration more generally with some ISS talks, and I believe some Mars talks as well. So, well, thank you very much, everyone, for your attention, and we look forward to connecting in other sessions. Have a great afternoon. Bye-bye.